Okay. All right. So you've just started touching upon things. Where are you in terms of optical activity? You said you have learned enantiomers. You've learned racemic
Yeah.
mixture, I suppose, then.
Yes. Yeah.
And you have learned diastereomers.
Yes.
You've learned mesomeric structure.
Meso. Yeah. We have done meso compounds. Yeah.
Meso compounds is also done.
Yeah.
And have you learned how to check if the structure given is an optical isomer of something or not?
No.
Okay. And what else have you covered so far?
That's about it. Yeah.
And what is the next topic which you're starting off with, or what does it look like?
I think calculation of calculation of optical isomers. Number of optical isomers.
Okay. All right. Okay. Okay. All right. Means I should not poke on this right now. So let me continue on with a little bit more of Fisher projection. So now Fisher projection is going to be something which is like Sawhorse. Sawhorse is basically the first version of your solid wedge and hashed wedge extension with more carbons. Fisher is a second extension. So let's talk about Fisher projection slightly more. If I'm having, say, a molecule which is going to be having, say, a carbon, one red and one white and two hydrogens. Okay, this is a molecule. What will the Fisher projection look like for now? If I'm drawing it, if I'm having it like this,
Will
which
be
one towards you here?
towards me will be these two hydrogens. So the
Yes,
hydrogens will
these
be
are
on
coming
the
towards you.
horizontal
The
line.
white and the red are going away from you. Right? So let's draw this projection now. Okay,
Yeah.
so sorry, this
It
is
will be like that. Yeah. But white will be
so white is above,
red
red
below.
is going to be here, hydrogen here, hydrogen.
HH.
So we're going to be having in this particular case here, these two are coming towards you, these two are going away from you. Okay, now let's draw the same thing slightly differently now, where we are going to be looking at how to perform a rotation here. We're going to learn what all are going to be the ways in which the same thing can basically be redrawn, such that it is not something which is going to be different. It has to be the same. First, let's talk about this molecule, then we'll go into an actual complicated one. This is an easy one. So first, let's look at let me draw a few more dummy templates. Okay. So let's rotate and see now what happens. I'm going to keep this. I'm going to rotate over here and see what's happened here. What did I do? How did I rotate now? I kept the red the same.
Yes. But you made the white towards.
I'm rotating the other three. Now what do you have? Which ones are coming towards you?
The hydrogen, sorry, the white and the hydrogen, yeah.
White and hydrogen. One hydrogen is away. Okay. So we're having a hydrogen here and a white here. And we are having a red at the bottom here. No change there. And we are going to be having a hydrogen. Okay. Wonderful. Now let's rotate once more.
Yeah. Now again same thing. But then the hydrogen's on the right side.
So we're going to be having white here. We're going to be
W,
having
H,
hydrogen
HR.
here and red over here. Okay. Now let me hold the white now.
Now the red will be coming towards us.
The red and the white are coming towards you.
Yes. Yeah.
Hydrogens are going away. So what is it that I'm doing here? In this here, I held the white constant. And what did I do? I rotated the other three.
Yes.
Correct? So the red effectively came towards. So the red moved here. What is happening?
Replaced by H.
Progressively, this fellow will go here.
Go there, this guy will come back here. Yeah.
You're understanding what's happening here?
Yes, sir. Yeah.
So let's now try to see if this is the correct thing which is happening. Because in this case, all of these are representing the same molecule. So this is not the best way to actually check whether this is going to be the case or not. Because in this here, everything which you can draw is actually the same.
Yeah.
That is, whatever I wish to put here, whatever combinations I want to put here, I can put any combination I want of the 4. I can put it as H, red and white. Or I can put it as red over here, white over here, H and H here. Or I can put it as red here, white here. Or no need to put it as white there. Huh? I can put it as red here, white here, H and H here. Effectively, the idea here is anything and everything which you can draw, everything is the same here. You are not going to be having any differences in any of the structures. Everything which you can put will actually be the same Fisher projection. Everything, all Fisher projections where you're putting 4 of these groups around the tetrahedral carbon will be representing the same molecule. Only difference is there'll be different rotational styles over there. Think of it like that.
Yeah.
Now though, if you have an optically active molecule, let's take a simple example of an optically active molecule and proceed there. So in this case here, I'm going to be introducing one more fellow here, a blue. So let's take this structure now. What is happening here? Which ones are towards you here?
Red and white.
Red and white. So let's draw them. In this particular case here, the red is towards my left, which is going to be your right.
Left.
Your left or your right?
Left.
Your left only, Adu. Okay, yeah. So left. Okay, so we're going to be having in this particular case here, the red is going to be over here, white is here, blue is here, and hydrogen is here. So from my point of view, let me just check up. No. This is ulta.
Yeah.
So blue, white. Okay. So this guy is white here. Red here. Okay. All right. So this is the structure.
Yeah.
Okay. Now let's try to see what is going to be the mirror image of this guy first. Let's try to understand the mirror image first a little bit more. You learn these are non-superimposable mirror images. Yes or no?
Yes, sir.
Did you see an example of that clearly enough?
Yeah.
Or it was something of this sort, or you saw it in
2D
hands mirror that type.
Hand.
Yeah. Okay, all right.
I think like this.
Okay. So this is the first one we saw. What was the projection we had there? Let's have a look now. So we had blue below and I had hydrogen above. So this was the projection we saw, correct? Now, blue and hydrogen above. This is the other one.
Yeah.
So this is the other guy. Now, in this case here, let me switch it to the hydrogens here and then show you the other way around. Blue up, na? Blue up.
Yeah.
If I try to superimpose them, as you can see, the hydrogen superimpose.
They don't match up.
The blue superimpose, but the white and the red do not match.
Yeah.
You understand the principle here?
Yes, sir. Yeah.
If I put a mirror in between the two of them, they will look the exact same in the mirror. That's the basic principle here. This is what is the actual meaning of mirror images. Now though, that means these two should be having a different Fisher projection.
Yeah.
Their Fisher projections should not be the same.
They are inverted. Lateral.
It should be inverted. Otherwise, if they're not coming out as inverted, that means there is something wrong in drawing Fisher projection. It should not be something which you should be learning then. Right?
Yeah.
So the purpose of learning Fisher projection is to make sure that it is the Fisher projection. Why we learn it is because it is the easiest to learn or understand optical isomerism. Sawhorse is easiest for generally understanding molecule. Newman projection is easier for certain other things. So, let's come back to this Fisher projection here of these two here. So the first guy we saw was blue below, hydrogen above, was this bugger. Correct? Now the fellow we are seeing is this fellow.
Yeah.
Now let's try to draw this fellow now. This is this guy, let us say. Okay, this looks more like the one we have drawn right now. So we'll keep it as this guy. This, let's say, is the other fellow. From the point of view of what I've drawn on the paper, white is here, red is here, white is here, red is here, we'll take it like that. Let's not be too accurate here, it doesn't matter. This is just mirror images, I need to explain here, it's okay. So in this particular case, the other guy is going to look like this. That is the mirror image for this compound, which is supposed to be a hydrogen here, a blue here, and we end up having a red here and a white here. Now, whatever I do to the first fellow, I should never be able to get the second guy. That's the idea here. Let's try rotating and see what happens. So the first guy here, if I'm taking this as the first structure, and actually this is the first structure now, I should check it like this only. So, okay, so let's take it like this itself. So from the point of view of drawing here, this was the first structure, correct?
Yeah.
Now let's try to go for the other possibilities of this guy. So what are the other possibilities? What do I mean by other possibilities? We can rotate the molecule, correct?
Yes.
So right now the blue is below. I'll keep the blue below. I will
about the blue. Yeah.
So originally blue and hydrogen were coming away from you. Now which is coming away?
Coming away are white and hydrogen.
No. White and hydrogen are towards you. Blue and
sorry. Blue and red are away.
So blue and red are away. So let's put the blue and red over here above. So blue is still in the bottom. Red now goes up. Correct? So what's happened to the other two here? The white has now taken the place of the red.
Yes.
Correct? So when the white has taken the place of the red, the white is coming here. And the hydrogen has taken the place of the white. So have a look as to what has happened over here. When you rotated, what did we do? We kept one bond a constant.
And we shifted the other three.
Yes. And how did we shift the other three? In any cycle.
Yes, cyclic manner, yeah.
It doesn't matter whether you go counterclockwise like this or clockwise. It doesn't matter. You understand the principle here?
Yes, sir, yeah.
So the idea here is when you want to check for the two structures drawn, now you can try checking. I want you to try drawing as many different ways of the first one. Let's call this structure number 1. Let's call this structure number 2. I want you to put pen to paper now. There is no unfortunate escape for this one. You will have to do this for yourself because me telling you will not convince you. Draw one every way possible by doing rotations. You understand how to do rotations now on paper on 2D?
So keeping blue constant.
It doesn't matter keeping blue or not. You keep one bond a constant every time you're doing blue. Rotation. Keep any one bond a constant, rotate the other 3. You understand what I mean?
So should I do that for all 4 bonds or like only do for
try for every possibility? I want you to try now for every possibility. Because this is something which you have to see. The understanding is also a set of points which you need to do by yourself. So draw the possibilities, every possibility for 1 and see if you can get 2.
Okay.
That's the goal here. Draw every possibility for 1 which you can mathematically draw now. How do you draw it? You hold one bond a constant and you rotate the other 3 in a cyclical or counter-cyclical manner. It doesn't matter how. Your job is to try to get the second structure if you can get the second structure.
Okay. So, yeah.
So, or have you already tried this exercise in your class now?
No, sir. Didn't try.
Then please do so now.
Yeah. Yeah, I don't think it's possible.
I know it's not possible, but I want you and your brain to make sure it is not possible by actually filling in the blanks there. Do them.
Okay. Yeah.
If you had already done this in your class, I would not have bothered.
Yeah, we didn't do it in class. Yeah.
So you need to learn this. This is, see, some of these, it's like addition, bro. You have to learn addition by doing addition. Mm. What's the situation? Have you have to convince yourself? Have you got
Yeah.
enough practice on drawing now?
Yes.
Need a lot more practice.
Okay.
But this is going to be one of the most important things which you will be learning for optical activity. Because when they're asking you to compare, is this structure the same as that guy? It's
Mhm.
not going to be that easy. They'll give you Fisher projections if they are nice. Sometimes they'll be not nice. They'll give you Sawhorse projections. When they give you Sawhorse, the
Mhm.
game is going to be you convert them to Fisher, then you check. Because what you do in Fisher is not applicable in other things. Fisher, this type of rotation is easy to do.
Yeah.
In Sawhorse, you try doing the same thing.
Second.
Draw a Sawhorse and try. Let's have a look at this guy in Sawhorse.
So, okay. Yeah.
Gets complicated, right?
Yeah.
Two are on a plane.
Hmm.
The fellow on the plane is also going to be changing.
Yeah. It's true. Yeah. It's
So
hard.
that's the point I was trying to make there. So Fisher projection is very efficient when it comes to handling
Rotations.
and understanding rotations individually and to compare for whether a molecule is actually what you've drawn is. And to understand the 3 dimensions of the molecule and optical activity in a far more better manner. Okay, now, so effectively speaking, this is basically a Fisher projection. Now, when it comes to larger molecules, it is going to be a far more complicated thing. You mostly will be doing this in the next session in your next 1 or 2 sessions in your school. So this should be a good refresher for that. Make sure that you are when you started learning optical you said you've done some optical activity now.
Yeah.
So far, some optical active molecules you've done with 2 or 3 carbon, right? By now,
Yes. Yeah.
try doing the same thing for 2 carbon type of thing. Let's take an example. That will be a far more better exercise for you actually.
2 carbon. Okay.
Let's take a simple one.
CH3, CH3. Yeah. Mhm.
Some red group. And methyl is also there. So this is unfortunately not optically active. What the fucker I am. So let's make it chlorine and bromine. So the mirror image for this is going to be this. Now,
So the previous one you drew was not optically active because it had a planar symmetry.
yes,
Okay. Yeah. This makes sense.
yes.
Yeah.
The moment I drew it, I realized what the fuck I did. So, okay. So you're still properly awake even after your lunch. You had lunch or you not had lunch yet?
No, sir, I haven't had.
I figured. If you think 2 o'clock is too early for your lunchtime, you could have mentioned 2:30.
It's fine, sir. Yeah. I have it here.
So that was your mom coming in the middle to give you lunch.
Yeah.
Eat, please.
Okay.
It's already
Yeah.
3 o'clock. You must understand that there are reasons for having food on a regular basis. You don't drink water also. You're young enough that your stomach is going to be highly acidic at this stage. And if you're not drinking water, that acidity, it can cause unnecessary troubles in later life. So, yeah.
Yeah.
Anyway, so you can snack on. Please keep snacking.
Okay.
I allow kids to snack on even in goddamn classes in real life. So, and food is necessary sometimes. Yeah, correct.
Yeah.
When I was your age and I had to attend physics classes like this, I used to sleep in the very difficult to keep myself awake in classes. So I used to sit in the back also. One of the things I used to do was I used to buy these chota wala 25 paisa ka, they used to be these orange wala chota candies. So
Hmm.
I used to stuff them in the bag and go and like put them in the mouth. Take a small bottle, this, put water in the cap, and then so survival mode. So since then I always felt like never food is allowed. It's okay.
Yeah.
Doesn't make a difference.
Yeah.
Coming into this year, I would like you to try to draw the first guy and try to see if you can draw that and convert it into the second guy in some way or another. Now, how to do rotations here? Let me give you a quick idea as to how to do rotations here. Let's say I want to do rotations on this larger thing here. Let's say I want to do rotation on carbon 1. Let's call this carbon 1, carbon 2. Okay, how to do rotation on carbon 1? I will keep this bottom half the same.
Yeah, that's it.
I will rotate these top fellows.
Yes. Okay.
You understand the principle there?
Yes, sir. Yeah.
If I keep the hydrogen the same, then I'll rotate the entire thing. Then the entire bottom will go up.
Sir, if you keep the methyl same and then you rotate about that, then
What will happen? One of them will go to the side. The long chain will go to the side there. That is going to be a complicated thing. That will be getting it out of Fisher projection predominantly there. So you'll have to rotate it back and get it back to the thing there.
okay. I see.
So that is the problem which comes when you're going to be having complicated Fisher projections. Do not do that type of rotation. You want to
Yeah,
do that type of rotation, do another rotation extra from a different angle. That's all. To do whatever you need to do. Make sure that you are avoiding rotating the big guy in the middle as much as you can.
Okay, yeah. Got it.
Practice rotations on this two over here. Or have you already done this in your school so far?
I did not do this, sir. No.
Not this. Okay. Then please do practice these rotations here. Just, it'll take like 1 or 2 more minutes. Just make sure that in your brain, you are convinced properly that 1 can never become 2. And I want you to try for this also. I want you to try drawing for this also. In this case, what's the idea here?
If you
They are supposed to be the same.
exactly, yeah. They are the same, right?
They are the same. It's optically inactive. Which means what should happen?
You can write one as
You should be able to draw it and get it to it somewhere.
exactly, yeah.
Go ahead, try.
Okay.
So these are not really things which I can teach and go about it. This is something which you'll have to actually mechanically sit and do. Try it out now because it will help out.
Yeah.
Convince yourself enough?
Yep, I got it. Yeah.
Second wala mila?
Yes, sir. Second one. Yeah.
Now, there are some neat tricks which we can learn. If I have something like this, okay, if I rotate the entire molecule, if in a structure which is like a single carbon, if they've taken the Fisher projection diagram which they are showing, if they rotate the Fisher projection by 90 degrees, then they are technically doing a mirror image of it.
Yeah.
If they rotate the Fisher projection by 180, they are actually showing the same thing.
Same thing. Yeah.
So that you have covered already?
Yes, sir. Yeah.
In your school, you have done that.
Yeah.
Very weird teacher, man. What the fuck? What the fuck? How are you supposed to understand it without understanding this? Seriously?
I didn't know that. Yeah. He didn't teach us this, sir.
He told you that though?
Yeah.
Okay. Now I'm getting a bad taste in my mouth a little bit. Seriously? This
Yeah.
was mentioned in your class that 90 degrees, that 180 degrees was given.
The 90 degrees was, yeah, you mentioned.
My next exercise was basically for you to try and confirm them with rotations.
Oh,
Now do them.
okay. Yeah.
So 90 degree tilt and a 180 degree tilt. You know what I mean by 90 and 180 now because you've done that in class.
Yeah.
I want you to do that and I want you to test them out with your sir with this rotation which you have learned now, how to do rotation. Because you have to connect the rotation with that first. Only then will you remember that is correct. Otherwise, that is just a goddamn piece of information. You will not remember it. So yeah, you not remember it, you not connect it properly. So make sure you test it out with rotation now. Take this guy and this is an optically active fellow. This is what to say, chiral thing, right? You know what chiral means, obviously, right?
Yes, sir. Yeah, SP.
The chiral carbon. So have you discussed what a chiral location is or a chiral molecule is properly?
Yes, sir. Yeah.
Chirality is?
Yes, sir. Yeah. Chiral molecule we discussed.
Okay, all right. Anyway, yeah, please discuss this part. Please try out this part here and finish up. Once you're done with that, we'll come to chiral a little bit. I have a couple of things I want to talk about that over there.
Yeah.
In fact, a better thing would be you can try for a big fellow.
Okay.
Try for a big guy, that'll be better.
Big guy? Okay.
Big guy, na?
Yeah.
The 2 carbon fellow.
Yes,
First, try for a simple one. That'll give you a clear understanding as to what it means. Try for the 180 degree one first. 90 degree one, don't waste time on it. Convince yourself it's a mirror image and move on. That should not take too much time. 180, you understand what I mean by that?
Yes, sir. Yeah.
Do you want me to show you for one of them or you understand what I'm asking you to try?
That can be shown once.
Okay. So let's say I'm going to be rotating this guy by 180 degrees here. So I'm going to be taking this fellow over here like this. I'm going to make it like this.
Yeah.
So I want to check if these two are the same now. How do I check if these two are the same? I want to get the hydrogen up there. So how to get the hydrogen up there? I will fix the white first. I'll bring the hydrogen up. So I'm going to be having white here. Hydrogen goes up. I'm going to be having red here. I'll be having blue here. So now I want to basically maintain the hydrogen there and then bring the white to this side and see what happens. So if I bring
R will come down, B will go there. Then we got the same thing. Yeah.
Yes, that's the idea here.
Okay, that's what you mean. Okay.
Yeah, that's what I wanted you to try out.
I
wanted you to try this out, not for the tiny fellow. For this year, 180 degrees ka convince ho gaya. Now for the next one, draw a 90 degree one. Confirm that that is a mirror image.
Okay.
Once you know it's a mirror image, you know it's not going to be possible to get it back to the original one.
Then
I want you to try the same thing out for this bigger fellow. Second compound. Take the second compound, invert the fellow by 180 degrees fully, and try to get that structure by rotation.
Okay.
If it is correct, then you should be able to get it. Correct?
Yeah.
Play.
Yeah.
You understand what I'm asking you to do?
Yes, sir. Yeah.
So
then if you had, suppose, a longer molecule and you rotate 90 degrees, it would look like...
You try. You're asking me the question which you're going to be having because you do not want to try and see what you can do there. Try, think what you should do there. Now you know the point which has to connect there, correct?
Yeah.
When you do it by 180 degrees, it should fit. You know it's supposed to be the same.
Yeah.
See what is correct there.
180 and it's number 9. Okay, I'll try 90.
We just tried 180 now for the Chota Wala fellow.
Yeah.
And it worked cleanly.
Yes.
So the 180 principle works.
Yeah.
This is why I told you what to say, if you remember them as a goddamn point, you're not going to be for sure. At some point of time, you'll remember it as, oh, 90 might be the same, 180 might be opposite. It will happen.
Yeah.
So that's why I'm asking you to sit and put your pen to paper and try now. You understand what I'm trying to tell you here?
Yes, sir. Yeah.
You remember 90 and 180 as an information. It will remain as information in your brain. Which means at some point of time, because it is stored as information in your brain will jumble it. Probability is there. If there are a lot of steps which you have connected, your understanding, your working is connected to that there, it will not jumble it up that easily. Or at least there is more friction for it to jumble it up.
Yeah.
So try now. You already tried for the bigger guy or you have not yet?
Bigger one doing it now.
I'll put the page there. You can try now. Try for the bigger fellow. You understood what I want you to try, yes?
Yes, sir. Yeah. Yes, sir. 180 is working for the larger one.
You got these two?
Yeah.
There is a red should be the same as a blue.
Yes. Yeah.
Got that done?
Yes, sir. Yeah.
So you understood what type of operation you have to do there?
Yes, yes.
You're rotating the guy also?
Yeah. Then keep one guy constant. And
If
then
you rotate
the
it,
guy
rotate it. That's all. Don't think too hard.
Yeah.
That is what you were asking me at that time, correct?
Yeah.
That's what I told you. Stop thinking. Stop thinking. When you think you want an answer, when you put pen to paper, it will flow. For someone as smart as you, it will flow. Your resistance is putting pen to paper. That's what it's going to be. That's your tough thing. That's why the point I mentioned originally, for you to start realizing that you are good at organic, you should have fun with organic. When you get bored, not like continuously sit and solve organic questions and have fun. No. When you're really bored, you solve like 2-3 questions. Okay, this is fun.
Yeah.
Ideally, you should be like, bore ho gaya, chemistry kar sakta hu thoda sa, us type aa gaya to bahut acha hai. But I'm not going to hope for that.
Yeah.
Okay. All right. Now, so you convinced yourself properly that 180 degrees is perfectly fine.
Yes.
90-degree turning is going to be a lot more irritating and complicated when you're going to be having that kind of a multiple carbon.
Larger. That's right. Yeah.
Let's not bother with that for now. That is something which you'll have to, come to terms with individually. Now, what else? That about covers things for now. I think that should be more than enough basics for today.